Hello. This is the first of a series of 6 lectures on non-commutative geometry. Non-commutative geometry that can be of many kinds. Things are not as clear as in the classical case. So in the classical case, right, the beginning of geometry was basic curves and surfaces like conics, cubics, and then all this evolved with the time. And the modern point of view is that such a basic algebraic manifold can be smooth or not. So we have a ramification here, and in case it's smooth, it can be Riemannian or not, a second ramification. So somehow things are quite well classified with algebraic geometry, differential and Riemannian. In the non-commutative setting, well, if you're motivated by quantum mechanics, you look at pictures of like electron distributions, all that, it's not clear where the geometry is. And if these elementary particles are supposed to travel on some trajectories which are non-commutative manifolds, it's not clear if what these manifolds are and if they are smooth or not. And if it's rather differential geometry or rather probability going on. So things are very blurred somehow. The geometry we'll talk about here, so it's definitely algebraic, right? At 100%. We'll do a lot of algebra with quantum groups, very algebraic. Well, let's put it 90% because it's not going to be very advanced like schemes or things like that. Just some fun with the basic algebra, a bit like the Greeks were doing with conics and cubics. So it's 90% algebraic. Smoothness, we'll be most interested in the free case, and there's not so much smoothness there, so a priori 0%. But let's put it 10%. There might be some smoothness there. And Riemannianity, and that's the big thing. So we'll be very interested in computing integrals over these manifolds, and only consider manifolds for which we have a good integration formula, Van-Garten one. So I think it's going to be 60-70% Riemannian, let's say. Okay, so once again, 90% algebraic, 10% differential, 60-70% Riemannian. That's the geometry that we'll talk about. And in relation with other geometries, well, this is extremely close to what Alain Cohn is doing. So Alain is looking at the Riemannian case. It's exactly what we want to. But with respect to him, so here we'll do much more algebraic geometry and no smoothness, almost no smoothness at all. Horn is with less algebraic geometry and more smoothness. We'll talk about all this unification at the end. So that's the idea. Now let's find this presentation. So we'll talk today about very, very simple things. I was telling you that well, it's not going to be schemes or stuff like that. We are not there yet. So we're trying to do things like the Greeks, let's say, look at spheres, very simple things. So today at spheres and Tori, commutative, and later on we'll build things, more complicated objects. So what's the idea? We mostly want to talk about free geometry, and the problem is that there is no free Rn or free Cn. If you just take coordinates without free coordinates, without any relation on them, you can do some algebra there, but there's no operator algebra. So there's no analysis there. So if you want a norm, for instance, on your free Rn, free Cn, it doesn't exist. The norm of these free coordinates are not bounded, so you cannot talk about norms. You can do anything. So instead of talking about free Rn, free Cn, which don't exist, we'll just get to one level below. So let's take Rn, right? We want to talk about non-commutative Rns, and we can't because these don't exist. So what are the objects in Rn that are somehow the most basic? And there are 4 of them. These are the sphere, very basic, the torus, unitary group, and reflection group, right? When you take your usual sphere around and the torus, which is actually a cube in the real case to be correct. The unitary group is the orthogonal matrices, and the reflection group is the hyperoctahedral group. So these are very, very basic things. And it's the same for Cn. Also, you have a complex sphere, complex torus. You know, it's your donuts, unitary group, and complex reflection group. And also for other examples, like in the free cases, you have analogs of these things. So the idea will be that non-commutative geometry for us won't be like Rn, Cn, and their free analogs, because these free analogs don't exist, but rather quadruplets of type STUK. Okay, so that's gonna be the first thing that I'd like to do. Axiomatize these quadruplets formed by a sphere, torus, unitary group, and reflection group. And then after axiomatization, we'll work out example, classification results. So we'll end up with a few geometries. And these geometries, we'll have to develop them afterwards, of course, looking at more general manifolds and like homogeneous spaces, all kinds of manifolds that we can have there. Then we'll look into integration theory and Riemannian aspects. And finally, well, we'll talk about the unification with the cone geometry. So once again, we're Riemannian here. We're interested in Riemannian non-commutative manifolds coming from operator algebras. That's exactly as Alain cone. So Alain is our big source of inspiration, but it's not exactly technically the same thing. So motivated by the same idea, same big principles. So manifolds must be Riemannian, must come from operator algebras. These are the things due to Alain cone. But we'll be more into like algebraic geometry and techniques, and also probability, and less into smoothness and Dirac operators and things like that. And as a general idea, well, Riemannian algebraic means geometry a la Nash, right? So that's how we're doing a kind of Nash geometry. And the idea for the unification, but we'll talk about it later in the final lectures, will be somehow to unify what we're doing with what cone is doing in the kind of framework of Nash cone geometry, which is very nice because this is exactly it. We're doing Nash and cone is doing cone. And Nash cone geometry, if you look at the initials, that's NCG, miracle. So this is probably it. The geometry physics is looking for. Well, we don't know yet, but that's our conjecture. Now let's get started a bit. Just a few slides with the explanations we want to do, then we'll get into technicalities. So as I was saying, the real geometry, so we don't want Rn, okay? We only want compact objects because we want sister algebras later. We want compact things. So the basic compact objects of geometry in Rn are the sphere, right? The torus. And the torus is actually a cube, and I'll take it to rescale like this. So it's just the two to the endpoints of the cube. I'll take it rescaled for it to embed into the sphere. Okay, we have the sphere and the cube inside. That's our torus, orthogonal group, of course, hyperoctahedral. These are the, if you want, the orthogonal matrices formed by permutation matrices, but sign 0, 1, -1 entries. Which is actually, there's a mistake there, HN. Mn 0 ±1 here. So these are the rotations of the coordinate axis in Rn, if you want. Now let's get to, so that's the kind of first quadruplet that we want to look at. Now we don't want the quadruplet, we want also the, how many, 12 correspondences between them. This will be our axiom somehow for non-commutative geometry. So we'll not get into that today, but let's just make this remark. Let's call it theorem that if you know enough geometry groups, things like that, very basic, you can establish the 12 correspondences. So for instance, how to pass from the sphere to the orthogonal group. The orthogonal group are the rotations of the sphere, right? Vice versa, the sphere is the homogeneous space. I mean, just take a point, rotate by orthogonal matrices, you get the whole sphere. So there's the passage here, and well, there are many others. For instance, Tn is a maximal torus inside On, so you can reconstruct On out of Tn. Hyperoctahedral group is a Riesz product of Z2 by Sn. This risk product brings semi-direct product of Z2 to the n of the torus by Sn. So once again, you can pass. Well, we'll have fun with this a bit later. But yeah, you can believe me. I mean, these four things are each of them is powerful enough as to reconstruct somehow the other three objects. They are somehow equivalent. Now let's take a look at complex geometry too, see if there are things going on here new. Well, the torus becomes a real torus now. Okay, when you put these conditions, you get a real torus of donuts. Unitary group, of course, complex reflection group. Once again, we have correspondences. It's pretty much what we were saying before. Same things, maximal torus here. Once again, are these products. Yeah, it's basically as before, no really new phenomena. So this would suggest, yeah, that we're on the good way. I mean, we just need to know what's a non-commutative sphere, torus, and unitary group and reflection group, and then to know a bit of yeah, these things like homogeneous spaces and quantum isometries and maximal tori, things like that. So as a preview, let's look a bit at the free real geometry. Let me explain in advance what will our objects will be. So a free sphere, this will be the manifold generated by, well, the functions on the manifold will be coordinates, which are self-adjoint, of course. Sum of squares is 1. So that's our problem to define. Same for n plus. You take self-adjoint coordinates and the matrix that they form is orthogonal. The torus will be the torus in a classical case is a cube. I mean, it's Z2 to the n. Now, if you want a free analog of that, that's it. You take the free binary group somehow and the dual of it. So we'll need that notion of abstract dual for a discrete group. And well, the hyperhedral thing is a bit more complicated. It's an analog of free, kind of free risk product and a quantum permutation group. So this is not hard to believe that it exists. And for those familiar with quantum groups, you perfectly know that these four things exist. But here comes my point, the correspondences, the 12 correspondences are trickier to establish than in a classical case. So there will be at least two new phenomena appearing, and we're going to have some troubles a bit in working out the axioms. That's for our next talks. Also, free complex geometry, that's another example, and the fourth example that we're motivating in. Once again, yeah, you can define that's quite natural for a free sphere. Unitary group, again, torus should be the dual of the free group. Complex reflection group. So all this, either you know or you can believe me, but the point is, once again, the correspondences are quite tricky. Things don't quite go like in a classical case, especially in the quantum group part here. You have to know a lot of quantum groups in order to construct these correspondences here, this triangle here. So that's somehow the plan. Now, what we need for talking about such beasts? Well, sister algebras, of course. So let's have a few small introduction to operator algebras. Well, I believe that all you know, but if you just vaguely know, that's the place for learning them. So that's the starting result. Bounded linear operators on a Hilbert space H. Bounded means that this thing is bounded. They form a complex algebra with unit denoted B of H, B standing for bounded, which is complete with respect to the norm. Why? Because you take Tn Cauchy, converges pointwise, it's fine. Has an involution given by this formula. That's exactly as for the matrix. Okay, the adjoint of the matrix, that's the formula. So it works too. And finally, norm involution are related by this, which means for matrices, it's like the biggest eigenvalue, absolute value to the square on both sides, so it's trivial. And in general, well, we just have to work a bit with the definition of the involution. It's double inequality exercise. So these are the operators on a Hilbert space. A Hilbert space, of course, can be finite or infinite. So the idea of sister algebras is that we'll just take these things here, what we found, that's going to be a definition for a sister algebra. So complex algebra with units, norm, involution, such that it's a Banach algebra in complete respect to the norm. and norm and evolution are related to this. Now, why is this interesting for us? We have this theorem of Gelfand stating that the commutative system algebras are exactly C of X with X compact space. So that's interesting because when the algebra is no longer commutative, we can think of it as being C of X with X being non-commutative compact space. So all these weird objects I was talking about, I mean, free spheres and everything, will be this kind of non-commutative spaces. Now, how to prove Gelfand's? Well, take the space of characters. And so first of all, yeah, why is Cx a sister algebra? Well, it's clear. I mean, the norm, the subnorm inversion, and just put bar functions. So now conversely, so it's a commutative sister algebra in C of X. Now conversely, take the space of characters. And of course, if you start with C of X, you get X itself. Now, in general, start with the commutative algebra. Well, you have a map like this, and you have to do some spectral theory, a few pages, like the basic theory of eigenvalues for matrices, generalize it in this setting, and you get tools, and you can prove that this is an isomorphism. So that's the result we'll be interested in, but let me tell you also about the other two results. There are three big theorems in sister algebras, the beginnings of Gelfand, the one we're interested in, and there's also GNS, Gelfand, Neymar, Segal, stating that actually the sister algebras, as axiomatized before, let's take a look there. So you see there's no Hilbert space here, it's abstract. These actually appear as algebras of operators. And well, how to do it? So in the commutative case, C of X, well, you can view it as multiplication operators on L2 of X. So in general, the proof is similar. You just need to construct somehow a measure on your non-commutative space, meaning integration functional on your algebra, what we call a trace. So you construct a faithful positive trace to be correct, and then you have this kind of construction like multiplication. That's the second theorem. And now the third one that is also important is in the finite dimensional case, we get exactly the direct sums of matrix algebras. Why is this true? Well, this is actually, you can prove it here. So Gelfand and GNS both require some spectral theory. So it's about 5 pages of ingredients for each. But this one we can prove it right away. It's very elementary, so let's do it. So I take a finite dimensional sister algebra. I write the unit as a sum of minimal projections. And then it's not easy to, well, no, it's easy to check that. So you take these things like the so-called corners of the algebra, PI, API. Well, these are, it's just clear. They're subalgebras of A, but they're not unital. I mean, their unit is PI. The inclusion AI into A is not unital, right? Now, well, this is not very hard to prove that you have a direct sum, which is non-unital. It's quite natural, right? Take the projections, and each of them determines a block somehow. Also, each block, because the projections is minimal, are matrix blocks. You prove that in a few tricks. So we're done. That's your decomposition. So these are the three results, and overall the whole package is it's like 10, 20 pages. No longer. When you look at any book on sister algebras or whatever stuff based on sister algebras, the 10 pages in the beginning is this. Explained with few details, so not very complicated. And that's actually what all will need, more or less, for developing this, this theory. Now, let's get back to Gelfand. So Gelfand was saying that commutative sister algebra means exactly C of X with X compact space. So now we have our definition. We can do non-commutative geometry, given an arbitrary sister algebra. We'll just write it A C of X and call X non-commutative compact space. So what do we mean by this? So these spaces are abstract things. They have no points. But besides that, they have everything. We can talk about functions on them and do a lot of things with them. And now, if you want to be if you're a very picky mathematician, so you need a category, right? So here's your category. You just take the category of sister algebras, but you reverse the arrows. That's by definition the category of non-commutative compact spaces. So perfectly well defined. Now, of course, we won't bother with categories, so we'll just use this notation, AC of X. And we can do basically everything with this, and even very advanced things like what Quan is doing, differential geometry, all kinds of stuff. So you can do many, many, many things with this definition. And we'll use, well, many people, there are two schools here. Some people use sister algebras, some people use non-commutative spaces as notation. It's exactly the same thing. Here we'll use, this is a bit more modern. We'll talk about non-commutative spaces. So for instance, whenever we have a morphism, we can speak of the morphism of spaces in the other sense. Given a tensor product that corresponds to a product of spaces. So it's yeah, it's just better to use spaces. And but of course, everything will always be about sister algebras, study of sister algebras. But we'll express everything in terms of the spaces because it's these spaces that we're interested in. The only thing to be kept in mind, these spaces are not points, but this won't bother us. And actually, if you look into like Lie groups, algebraic geometry, all that, you don't take that often a point in a group or in a manifold, right? Use a lot of algebras and whatever Lie algebra schemes, things like that. So it's the same idea. And finally, your points, you don't really need them with algebra. Anyway, you need algebra for that. Now this, yeah, let's construct some spaces. So free spheres. You see, I take the sister algebra generated by x1, xn, self-adjoint sum of squares is 1. And, well, I take the star algebra to begin with. On the star algebra, you see the coordinates, the norms are bounded because this quadratic relation here is the sum of positives, which is 1. So each of these positives has norm less than 1. So the norm is bounded, so I can consider the universal sister algebra with respect to this biggest sister norm abstract, and I call it C of Sn minus 1R plus. So if you want, that's the definition of the real sphere as a non-commutative space. Same for the complex one. So here, well, we have to put two relations. That's a bit tricky instead of one because the first one doesn't imply the second one. And yeah, it looks better with both. Let's take it like this. So we have our three spheres. Now what we can do with them, some basic things. So these things appear as liberation somehow of the real and complex spheres, the usual one. So let's talk a bit about that. What do we mean by liberation? So given any non-commutative compact space X, right? This comes from a sister algebra, C of X, and I can divide that sister algebra by its commutator ideal. Well, what do I get? A commutative sister algebra. So by Gelfand should be functions on something, and that's something I call it classical version of X, and I will denote it X class. Okay, so any non-commutative space has a classical version, and we'll say that the non-commutative space is a liberation of the classical version. So let's go back now to the sphere. So we have to prove this. This is not exactly trivial from what we said. So the free spheres appear as liberations of the classical ones. So what do we mean by this? Let's take the real one, the free real sphere. So if I divide by the commutator ideal, which means exactly to take this algebra here, that was the algebra of the free sphere, but now I added com, means universal commutative algebra. That's exactly modding out by the commutator ideal. I must prove now that this coincides with the functions on the real sphere. You see, there is something to be done here. The same in the complex case. Well, but this is clear by Gelfand. So let's take the real case. So you see this universal algebra here is commutative. So by Gelfand should be functions on something. Now on that something you have coordinates which are self-adjoint sum up to 1, the squares. So it can only be the sphere, right? And same in the complex case. So this is, well, after all, it's a triviality if you know Gelfand. If you don't know Gelfand, of course, you cannot really do it. But yeah, it's a triviality modulo Gelfand. So that's our first theorem, let's say, about spheres. Now, let's get into Tori. So same thing. So you take self-adjoints whose squares are 1 over n. That's like a cube somehow, and a free cube, and the free torus is like this. So once again, here you can draw a lot of diagrams. We won't do all of them. So as for the spheres, disappear at liberations. That's clear, same argument as before. Do Gelfand and compute what you have. And also the tori embeds into the spheres. Remember, the tori in the classical case were normalized as to fit into the sphere, right? And the good size. Here is the same. So you see, xi squared is 1 over n. This means that sum of xy squared is 1. So this embeds into the real sphere. The same in the complex case. So you have embeddings, and actually in the other sense too. So given one of your spheres, you can recover the torus just by intersecting with the free torus here, the big torus somehow. So okay, you can draw a lot of diagrams. We won't bother with that. So we have liberations and passage from the tori to the spheres. Now the problem is, we'd like to understand what these spheres and tori are. And the spheres, well, there's nothing much can be said about them. These are new things, but this tori, for those who know, you see, for instance, a complex torus says definitely this is algebras generated by unitaries. It must be group algebras. So let's talk about group algebras in order to identify these things. So what's to be known here, I take a discrete group and consider the group algebra, the usual one, involution making the group elements unitaries. Then here, of course, I have a C-star semi-norm because these guys are bounded by 1 in norm, being unitaries. But that might be a semi-norm. Of course, you have to prove that it's a C-star norm. I mean, it doesn't vanish. And once you have that, of course, you can close with respect to the norm, and you know it is C-star gamma, the group algebra. So in order to prove that the semi-norm is the norm, that's the only tricky points. Well, you use the left regular representation of the group. You see left multiplication exactly like for GMS before. And well, this is an embedding. I mean, it's not very complicated. So that's why your semi-norm is actually a norm. So this is the algebra contains faithfully somehow the visual group algebra. So you see, these are system algebras generated by unitaries. It's very similar to what we had here. Also, system algebra up to Tori scale generated by unitaries. Now, let's talk a bit more about this group algebras. So when gamma is abelian, what happens is that, of course, start of gamma is abelian. So we can apply Gelfand. Now, if you compute the spectrum, this means characters. These are actually the characters of the group, right? By linearization, delinearization. So you get the functions on the group of characters, which is the so-called Pontryagin dual, denoted with the hat. So, well, now following our general philosophy in general, and gamma is no longer abelian, write exactly the same formula and call G abstract dual of gamma. It's a non-commutative compact space. So again, yeah, we can talk about group duals, and in abelian case, these are exactly the Pontryagin duals. Now let's get back to our tori. So where were the tori? So up to normalization, up to rescaling here, these are group duals, right? And here's the results. So these are our 4 tori, real, complex, classical, and free. And they are as follows. So the free ones that we're interested in are duals of the free group and the free binary group somehow. In the classical case, that's the cube, but in Fourier somehow, and that's the torus also in Fourier. So why is this true? Well, I mean, you just take the algebras there where they are. Let's go back. Yeah, here, these are group algebras and the relations. Here you have no relations. I mean, it's just generated by some unitaries, so you get the free group. And here is the free group modded out by the fact that the generators must be self-adjoint. This means that all the z's become z2s. So you get these things here. The classical case, of course, is so you get these algebras, right? These group algebras. And now our convention is that the non-commutative spaces associated to this are just the corresponding discrete groups with a hat. Yeah, we put the hat to get this. So very nice. So we have toroidal spheres. That's very good for today. And next time we'll talk about the other components, unitaries and reflections. But there was a bug actually in all we've been talking about today. So let's end with this philosophical discussion. So if I take a non-minimal group, well, for those who know, like the three groups, you can prove that this map from C star to C star reduced is not an isomorphism. So this means that you see I have two algebras which are not the same, but both somehow they correspond to gamma hat. So that's a bit of a bug. I mean, yeah, gamma hat. These group duals, finally, they're somehow multi-represented as non-commutative spaces. So that's what's the fix to this. And actually, the bug appeared even before I told you, right after Gelfand, that we can talk about non-commutative geometry, we can talk about products, all that, but this corresponds to tensor products at the level of sister algebras, and there are several tensor products there actually. So there's the same situation as here, even more elementary. So yeah, you have to be careful. So now, because we'll talk a lot about these non-commutative spaces, let's fix this bug. So there are several fixes. One of them is to like this. You talk about measure spaces. So this corresponds to sister algebras with traces, and the trace is not even needed to be faithful, because you can always make the GNS construction and replace your algebra with that. And this works for group duals. I mean, let's go back to this, to our bug. So here you have a trace, of course, and the trace actually comes from the reduced algebra. Well, it's a bit technical for those who know. And yeah, so the trace comes from the reduced algebra. So when you do GNS, I mean, you get the reduced algebra in both cases. So the bug is fixed in this category here, which is a bit, it's a quotient somehow of the category of non-commutative spaces. As we define it, it works. So that's very good, but the thing is that, well, for spheres, other things, we don't have yet a trace, we don't know how to integrate over the sphere. And that's tricky. So this is a fix, but it's not exactly, we cannot use it right away because we don't know for the spheres how to integrate over them. Now another fix is to, exactly as before, but you can talk about von Neumann algebras. I mean, let's have the go until the end there. So this is somehow a bit non-natural. Sister algebra of faithful traces. Obtaining GNS are definitely gonna close under the weak topology. And yeah, for those who know, these are other types of operator algebras called von Neumann. And the commutative ones are exactly an infinity of X, the X measured space. So that's another fix. Once again, looks for group algebras. You get the group von Neumann algebras, which are unique. I mean, there's no fear reduced, but it works for the group duals. But for spheres and other spaces, yeah, we have no trace yet, so we cannot use this fix. And well, the third and the good fix that is very nice is the following. So in all that we'll be doing, everything will live inside this free complex sphere. So all the spheres live there, right? The real one, and also the tori live there, right? So everything lives there. And all we'll be talking about, all these 6 lectures, we'll be talking about things inside the free sphere, and more precisely real algebraic manifolds of the free sphere, meaning that there C of X is a quotient by some polynomial relations between Xi and their adjoints. So we're talking about real algebraic manifolds of a free sphere. And for these manifolds, we can simply identify them when the corresponding star algebras are isomorphic generated by coordinates. You see, I mean, it's as dumb as this. So this works for the group duals because, let's go back here. So what are the coordinates of these guys? Are the GIs, right? So what are the star algebras generated by the coordinates? These are the usual group algebras. I mean, algebraic group algebras, not completed. So it's the same, I mean, on the left and on the right, right? Any group has a unique group algebra in an algebraic sense. And that's why our fix is good. And it doesn't use anything like a measure, and it works also for the spheres. I mean, if you give me a, well, don't we don't know yet what's integration, but we'll learn later that there are some versions of these spheres also somehow fully reduced. For this definition, the spheres as the groups are uniquely determined by this. Okay, so this is pretty much it. So now getting back to the plan in the beginning, what did we do today? We did a very first part of step 1. We have objects, at least classical and free, spheres and tori, but it was the hard thing to start with, because in the next lecture we'll complete UK and also start to develop all these correspondences, and then we'll get to steps 2, 3, 4. So that was it. So once again, yeah, this was quite algebraic today, but we're doing algebraic geometry, but we'll get into more analytic aspects later. First, to do all this algebra, we'll get an integration and somehow Riemannian structure later. So see you soon for next presentation.